All right, friends, I hope you took your vitamins this morning, your seatbelts are fastened, and you're ready to go because we got some ground to cover today. I just wanted to finish up on carbocation rearrangement. There have been some questions. How do I know when this will happen? And the idea is you're looking for a secondary carbocation adjacent to either a tertiary or a quaternary carbon. Those are situations where a 1,2-methyl, a 1,2-hydride, or a 1,2-alkyl shift can lead to a more stable carbocation. How do I know which to do? Well, do the one that leads to the more stable tertiary carbocation. For example, here I showed you how if you do a 1,2-methyl shift with one of those methyl groups that's adjacent to the positive charge, you get a more stable tertiary carbocation. Having done that, then I talked to you about how to draw the elimination products that come from that carbocation. How do we know to expect elimination products? Because we're using TSOH or H2SO4, and those give exclusively alcohol dehydration products or elimination products. Now the tricky one was this one. I showed you that if instead of moving a methyl group over, you moved over carbon 6, that would still give you a more stable tertiary carbocation. But in this case, that would have involved, instead of the methyl group coming over, rearrangement that shrunk the size of the ring from a 6-membered ring to a 5-membered ring. Now, there's been some confusion. Is that good or is it bad? Does it want to do that because of the ring strain or something? No, it's simply because you're going from a less stable secondary carbocation to a more stable tertiary carbocation. But surely the change in the ring size must do something, the question is. And the answer is, well, actually not for 5 versus 6-membered rings. You'll learn that 6-membered rings, because of the chair conformation, are really not ring strained at all. There is a small but basically minuscule, not really worth worrying about amount of strain in a 5-membered ring. So there's not a huge change in like ring strain when you go from 6 to 5. The major change here is that you get to go from a secondary to a more stable tertiary carbocation. Now, some of you are having trouble visualizing this, and that's okay because it's difficult. It's deliberately hard. You're going to need to spend some time with it. One of the things you might consider doing while you're trying to get your head around this is to abbreviate carbons 3 and 6. Let's just call them R groups instead of, we'll leave the numbers there because it's not hurting anything. We'll call this R and R prime. If we get rid of the ring and then we simply show, oh, it's the R prime group that's shifting over to give this, then it's not such a big deal. You see that that's just a 1,2 alkyl shift. And then you can go back in and remind yourself that R and R prime are actually attached to each other. That maybe simplifies things a little bit. So that's just an alternative way of thinking about it if drawing the ring switching like that is a challenge for you. Yeah?
So, I don't know if you already talked about this, but when you're just like switching a carbon bond, does it have to do with like the orbital theory?
Yes, it does. The question is, when this is happening, does it have to do with molecular orbital theory? The answer is for the 1,2 shift to happen, the carbon-carbon bond that's going to shift over, or a carbon-hydrogen bond that's going to shift over, has to be able to line up with the empty p orbital by hyperconjugation, and then it just leans over completely. Yeah. Yes?
Isn't that hard to do with the constraints of the ring?
Is it hard to do with the constraints of the ring? If you built a model, it's possible.
Okay.
Yep. Yes?
Okay, I'm going to see an example if there's a 6 to 5 ring and
You could imagine a situation where you could set up an exact analogy of this situation where it's a 5-membered ring. Could you go to a 4-membered ring and get to a more stable carbocation? That sounds reasonable. I'm worried about it because ring strain is an issue for a 4-membered ring. So you'd have to balance the idea of improved carbocation stability versus decreased stability of the ring. I don't exactly know what to do there, so I'm going to punt and just not give you that one. Okay. All right, yes?
So will this happen every time, either the 1,2-methyl shift or going to the 5' ring whenever it's going to give you a more stable carbocation?
So you're going to look for carbocation rearrangement to happen anytime you have a secondary carbocation adjacent to a tertiary or quaternary carbon, and the 1,2 rearrangement gives you a more stable carbocation. Yep. So having done that rearrangement, now you will look, because this is a dehydration or elimination reaction, you'll look for protons that are adjacent to or beta to the positive charge. There's one here, and then there's another here. And you will draw elimination products that come from removal of those protons. Now, I'm not going to ask you whether the rearranged products are major versus minor relative to the non-rearranged products. If I asked you to choose the most stable alkenes, you could certainly do that. The pink one and the orange one are more substituted and therefore more stable. If you had to pick a major product, it would probably be these two. But I'm not actually going to ask you, well, is this the major one? Are these the major ones? Are these the major ones? You'll simply draw them all. And there are 6 of them, so that's fun. Now, why are we, go ahead.
Is TSOH still what's going to remove the beta?
So what removes the beta hydrogen? Yeah, it's likely either the conjugate base of, what is the base here? It's likely the conjugate base of the acid, or if you were doing this in H2SO4, it could be water. So yeah, the base in this case is likely the conjugate base of TSOH. Yes?
Within this reaction proceed E1?
Yes, and because it involves a carbocationic intermediate, we would call it E1. Yep. Okay. Now, all of that to say, reactions that involve carbocation rearrangements are fun, but if you want one desired product, it's kind of a mess. And so we need a workaround. We need to avoid the carbocation rearrangement. So that's our theme for today. Let's start with substitution reactions of alcohols that avoid carbocation intermediates. And there are going to be 3 of these. Now, at the outset, I'm going to be introducing 3 new reactions, 3 new reagents. You're going to have questions about why these reactions work, and I'm going to have an absence of answers. The strategy in each of these is going to be turning the OH into something that's a good enough leaving group, but not good enough to leave on its own before it gets attacked by the nucleophile. You're trying to balance leaving group goodness, and if it gets too good, maybe the leaving group just leaves without the nucleophile attacking. If the leaving group does leave without the nucleophile attacking, you've got a carbocation intermediate, and that's a problem. So we're fine-tuning things here, and when you're fine-tuning things, sometimes you find something that works and you're not sure why it works. So we'll go through these individually, and I'm going to try to help you understand what happens and how it happens, but we're not going to have great answers for why it happens. So at the outset, let me just give you some strategies you can use to help you remember details that are empirical or that don't have a really good answer why. In such cases, you may just have to memorize some things. So if you have to memorize something, one way to do this, if you like flashcards, is to write a flashcard where you have a starting material and R here is for reagent, and you make yourself guess what the product is. That can help you remember what the reagent does. An alternative flashcard, which is also useful, is for you to see what the starting material and the product are, but to not see what the reagent is, and you have to fill in or guess what the reagent was. That can help you think backwards, think in terms of what reagents do and how they convert starting materials to products. And then a third format is to take a product and a reagent and think backwards to what the starting material might have been. So you might want to do that for each of the four sort of new reactions we're going to do today to help you memorize details where we don't have a good explanation for why. Okay, the first reaction is going to be to convert an alcohol to an alkyl halide using a reagent called PBr3. That's a phosphorus bonded 3 times to bromine. If you want to see the Lewis structure, there it is. Essentially, what this reaction does is it converts the OH into a good leaving group, but it's not a good enough leaving group to leave on its own. And so then Br minus acts as a nucleophile, attacks the good leaving group, and the leaving group leaves. And what you observe here as the product is Br in place of the alcohol with inversion of configuration. So when you use this reagent, the result is that Br replaces OH with inversion of configuration, consistent with backside attack at the carbon where the oxygen was. And so the conclusion is that it must be SN2. That is, the leaving group must not leave on its own until the Br minus attacks. Yeah?
Is the H just kind of, is it not using everything in this case, or is it just kind of sitting there and we're assuming it's all that one step?
So I haven't shown you what the structure of that leaving group is. You're wondering where the hydrogen went. If you want to see the structure of the leaving group, here it is. And the mechanism for formation of that leaving group is actually just the oxygen attacks the phosphorus and bromine leaves. I'm not going to draw that mechanism for you. It is in your text if you want to see it, and that may be helpful to you. I found, though, that it's just more details that tend to bother students, and what everybody asks is, well, do I need to know it for the test? And I'm like, I don't care that much, so I'm sparing us all that awkward dance, shall we? If you want to see how this happens, the mechanism is in your text, but I'm not holding you responsible for it. But you better know that this reaction converts OH into a good leaving group, and then Br replaces that good leaving group in an SN2 reaction. Okay? What you're not going to know is why that leaving group didn't leave to give a carbocation. Why did it have to wait for Br minus to attack? I haven't got a good answer for you there. And this is the state of affairs in organic chemistry. A lot of times when we find a new reaction, and this isn't a new reaction, it's actually really old, but when we find a new reaction and it works, we often can use it and we know that it works before we know why it works. And sometimes you have to do a bunch of follow-up experiments to determine why something works. In this case, we don't care. Yeah?
Does this have a special name like the TSOH?
Does this have a special name like TSOH? No, just PBr3 is the reagent. It's, but you can think of it as conversion of an alcohol to an alkyl bromide with inversion of configuration. Okay, now this allows you to do a two-step synthesis. For example, If you wanted to replace the OH with something else besides a bromide, you can now. You can take the alcohol, you can use PBr3 to get the corresponding bromide with inversion of configuration, and then you can do whatever SN2 or E2, or even if you're crazy, SN1 or E1 reactions that you normally have done with alkyl halides. For example, if I wanted to use CN minus, which is a good nucleophile but not a good base, I could get this product. Or if I wanted to use tert butoxide, which is a good base but not a good nucleophile, I would get a mixture of these elimination products. So it's a way to join, it's a way to get from an alcohol to an alkyl halide, which you've done stuff from chapters 7 and 8 with alkyl halides before. Okay, so that's the first one. The second one is like unto it. It's basically exactly the same, only we're going to use a different reagent that's going to replace the OH with a chloride. So this reagent is called SOCl2. And for this reagent, we also have to include a base called pyridine. Why is the base necessary? And the answer is, I don't know. Why didn't we need a base for PBr3? I don't know, and the text doesn't really provide a good explanation. As I said, when you invent a new reaction and it works, sometimes you optimize it to make it better. Like you'll start adding a few things, much in the same way that if you're in the kitchen cooking, you're like, let's add a little bit of salt there. The recipe doesn't say to add salt. I know, I don't care, I like salt. You add salt to it, it turns out better, you're like, yay. And then if you're nice, you put it on the recipe. If you're not nice, you leave that off the recipe. So when you bring the thing to the event, it's always better when you do it instead of when people who you've given your recipe to, right? Anyway, that was a weird, how did we get there? Sorry. Anyway, so when you invent a new reaction, often you add some things to try to optimize the yield, and in this case, it must be that the pyridine helps the reaction go better. In any case, what this reaction does is, again, it replaces the OH with the chloride, and again, you see inversion of configuration consistent with backside attack. Therefore, the mechanism must have involved SN2 attack of Cl minus on a good leaving group. And so essentially what's going on here is SOCl2 converts the OH into a good leaving group, and then Cl minus does backside attack. Now, if you want to see what that good leaving group is, I'll illustrate it for you briefly. It looks like this. Where did the hydrogen go? Pyridine removed it. Why was that necessary here and it wasn't necessary with PBr3? I got nothing. The key step is that you get backside attack of Cl minus on the good leaving group. The leaving group leaves and you get inversion of configuration. Some people like to pronounce these reagents rather than saying SOCl2, so if you want to call it SOCL, you are welcome to do that. Okay, and you could use SOCL in a same two-step synthesis like we've done here. You can do, with this alkyl halide, any of the things that you can do in chapter 7 and 8 with alkyl halides. Okay, so that's two, and they basically work the same way. You turn OH into a good leaving group, and then you have a nucleophile, either Br minus or Cl minus attack from the backside. Go ahead.
Are there nice names for these reactions?
Nice names for the reactions.
Like a title kind of thing?
You want a title. If I gave it one, it wouldn't help. So conversion of alcohols to alkyl bromides. Because these, go ahead.
I was just gonna ask, what is it again that makes it a good leading group? Is it just whatever is attacking
So the reagent, PBr3 or SOCL, is the thing that converts OH into the good leaving group.
And what is it about those reagents that makes it?
Yeah, what is it about those reagents? I applaud the question. It's really good. I don't know that I have a great answer. I will punt. I will give you a brief answer, but it's not anything to worry about. Oxygen-phosphorus bonds are actually strong, so it's pretty energetically favorable to do this. That's what makes the new bond between oxygen and phosphorus, and bromide has to leave from phosphorus when that happens. As to why this is a good leaving group, remember what makes a good leaving group good is it can tolerate the extra electron density when it gets when the bond breaks and these electrons leave with it. Good leaving groups are conjugate bases of strong acids, so that must be the space that we're in. If you want to ask the question, why doesn't this leave on its own to give a carbocation? I'm like, well, it must be not as good a good leaving group as water was before when we did the chemistry. But you want to know why that is? That's like, I don't know. Okay, did I see another hand? Yeah.
The SOCL and pyridine reaction,
Yeah.
you said that the pyridine removes the hydrogen.
Yep.
So is that
So,
present for this to happen?
right. Does the pyridine have to be present for this reaction to happen? My guess is the reaction goes better if it does. What I'm talking about is the SOCL reagent, and I'm not holding you responsible for this, looks like this. The first step of the reaction is basically oxygen attacks the sulfur and then chloride leaves. That would give you an intermediate that looks like this. Pyridine then removes that proton, which gives you what I drew you, and then that's the good leaving group. So all of those are details if you want to delve into. They're in your text, feel free, but they're not details that I'm going to ask you about. But you must know that the nucleophile attacks the leaving group from behind in SN2. Okay. Now, let's give you an interesting conundrum. Suppose you started with this alcohol and you wanted to get this product in which an azide nucleophile has replaced your alcohol. And you know, okay, I need to turn the alcohol into a good leaving group. And then I need to replace that good leaving group with the azide. It would make sense to use a strategy like this, where first you use PBr3 to do SN2 chemistry to replace the alcohol with Br, and that involves one inversion step. And then you could bring in the nucleophile, which is N3 minus. We've used that as a nucleophile before. And this would be a second SN2 inversion step. Okay? In effect, we've replaced OH with our nucleophile here, and it almost looks like we've got retention of configuration because the OH group that we replaced is a wedge, and the nucleophile we replaced it with is also a wedge, but we've done it by double inversion. Do you see how that two tandem SN2 reactions give you a nucleophile in place of the OH group, but it's still a wedge? Making any sense? Yes, go ahead.
So when there's the same stereochemistry with the reactants and products, we can assume that there's two backside attacks or two SN2 reactions.
Right, if you replace this OH with a nucleophile and you have the same stereochemistry, the one way you know of to get there is two SN2s, two backside attacks. Do we need to close that door? That's starting to bother me. the grounds department is trolling us. They know we're trying to do OCHEM in here, and they're standing out there, distracting you, just preparing you for the rest of your life. Mom, 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 dad, 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 dad. Or in my case, my 17-year-old's writing his essays for his BYU application. It is, you guys will remember how that was. It is so painful. And he's trying to do this last night. He comes home from his job and he's like, okay, I need to hit it. And his brother's upstairs, band practice. We got the drum set going. We got a bass. We got a guitar. They're winding their way through Weezer's "Say It Ain't So" at the top of their lungs. And anyway, I told them, okay, go take a break, put on your noise-canceling headphones. Band practice is over at 9, and then you can get started. So anyway, we were distracted, but we're on it. Now, double inversion. You get that? You have to do 2 tandem SN2s. Now, yeah, go ahead.
The 1 and 2, I thought underneath an arrow was like an solvent.
Yeah, so there's generally, there's no real meaning attached to underneath and over the arrow. Organic chemists will be sloppy about that. It is true sometimes you'll put the reagent above the arrow and solvent below the arrow. When reagents are labeled like this, that communicates 2 separate reactions that I'm doing in a row, and I'm just saving space by not writing them out individually. Yeah, yes? Is everything in the same solution? Generally, no. When you number things, that means you do this one first, you isolate this product, and then you do the next reaction after. Yep. Okay, so what if you wanted to take that same alcohol starting material and you wanted to get the stereoisomer where the azide was a wedge? What are you going to do there? Now, somebody out there has the idea, let's just do 3 inversions. And that would work, but that might be wasteful if there's a way to do it only once. So I'm going to introduce strategy 3, which is a way to convert the OH into a good leaving group and do so in a way that allows us to, so we want magic step 1 that's going to give us this, so that in step 2, when we add the azide, we can just do a straightforward SN2 reaction. Yep.
But don't we want retention of configuration, or does it not really matter?
Sorry, so I'm setting all of this up by saying getting this retention of configuration by double inversion is pretty straightforward. Doing this reaction where we replace the OH with the nucleophile and we get inversion of configuration is a little trickier, because the only way we know of so far to turn the OH into a good leaving group involves inversion of configuration. So the azide attack is always going to involve inversion of configuration. The question is, can we turn the OH into a good leaving group without inversion of configuration? So we don't have to do double inversion. Yeah?
Because I mean, it's N3 minus.
Could I just add a hydrogen to the N3?
And then have the O pull off the H.
If your strategy is, can I protonate the OH group? If I do that, I'm into SN1 territory, and then I lose configuration entirely. So there is a solution to this. And the solution we'll call our method 3 for turning OH into a good leaving group. Using TSCL to convert, and I'll tell you what that is, ROH into a good leaving group without inversion. And the secret is the carbon that the OH is bonded to in this reaction is not involved and is not attacked in the reaction. So what is TSCL? That stands for paratoluene sulfonyl chloride, or TSCl. Its structure is this. It's related to TSOH. So not to be confused with TSOH. And it looks like this. It's a benzene ring with a methyl group attached, and then on the opposite side, or para to that methyl group, you have a sulfur. The sulfur is doubly bonded twice to oxygen, and then here you have Cl. And it turns out TSCl is an electrophile, and it's going to react with your alcohol, which is going to act as the nucleophile. This is the reason, okay, well, let's see. So I'll show you this mechanism, but again, I'll show you this mechanism so that you understand why there's no change in stereochemistry at the alcohol, at the carbon of the alcohol. So the oxygen of the alcohol attacks the sulfur and the Cl minus leaving group leaves. That gets you to this intermediate, which I will draw like this. There's still a proton on the oxygen. And it turns out that you need also to include a base, and the common base is pyridine. Pyridine will remove the proton, and that will give me my product for this reaction. And the product looks like this. Because we get tired of drawing all of that, we will abbreviate what's in gray with the letters TS. Okay. Now, at that stage, we are done. This is a stable product. And notice that in no case did anything attack the carbon that has the alcohol. In no case did anything do backside attack on the carbon that has the alcohol. Your question might be, why not? Because if you noticed here, OH minus kicked off Cl minus from TSCl, so why doesn't Cl minus come in from the backside like we saw before with PBr3 or with Sokol? And that's where I don't have an answer for you. It apparently doesn't happen because you can isolate this product, which is called in your text, this is called a tosylate. And the tosylate itself, this including the oxygen, is a good leaving group. And it sort of looks like an avocado, maybe? Anyway, now it does. The tosylate is a good leaving group, but not good enough to leave on its own to give a carbocation, and certainly not good enough for Cl minus to come in from the backside and attack. So, because the because the carbon of the alcohol never got attacked, there's no inversion of configuration, and so we can now do the reaction described above. Now, I don't think let me just show you how I drew this mechanism so you'd understand how this reaction works, but I'll just show you how you would write this. TSCl and pyridine gives you the OH now is a good leaving group with no change in stereochemical configuration. So now you can go back and do what we wanted to do above, which was, and you can do with this tosylate, you can do anything from chapters 7 and 8. This basically reacts as though it were an alkyl halide. So you can do SN2, you can do E2 type chemistry with it. It wouldn't make sense to attempt SN1 and E1 chemistry with the tosylate, because if you wanted a carbocation, you should just use the chemistry we talked about last time. So in this case, we're using N3 minus. That does do SN2. The tosylate gets removed, and so we do the two reactions, the first reaction, the second reaction. There's only one inversion step, and so that's why we're able to get the desired stereochemistry. Yeah?
So, is the main difference between the third one and the first two just the fact that there isn't backside attack from the chlorine?
Yep. Yeah, the major difference between the first two and the TSCL is that there's no backside attack by Br minus or Cl minus. Yep, that is the major difference. Let's see, you first and then you. Yep, go ahead.
Does that mean that N3 is a good base?
Yeah, N3 is a weak base that's a good nucleophile, which is why I'm not showing you E2 products. Yep, go ahead.
So, just the reason that we retain this electron configuration is because we keep the oxygen there.
Yep.
So we can just tell that based off of the TSCL.
That's right.
Okay.
You'll need to remember that TSCL gets you to something where the OH is now converted to a good leaving group, but there was never any backside attack. All right, some quick reminders of things that I didn't say earlier for the first and second reactions. Because the first and second reactions, PBr3 and Socyl, involve SN2, we're really only going to do them with primary and secondary alcohols. If you wanted to use a tertiary alcohol, you should just use HBr or HCl for these reactions. The whole point of using PBr3 or Socyl is to avoid a carbocation intermediate. Similarly, for TSCL, you could do this with primary, secondary, or tertiary alcohols, but again, you have to be a little bit smart. If you make a tertiary tosylate, you can't do SN2 with it. So, more power to you if you're trying to do elimination chemistry. But if you're trying to do substitution chemistry, that's a bad plan. All right, finally, we need to introduce the last a method for doing elimination reactions of alcohols. Without a carbocationic intermediate. And as before, this is going to involve a new reagent that's going to effectively do an E2 reaction without you having to worry about a carbocation. To illustrate this, we're going to start with an alcohol where in the past, if you used H2SO4 or TSOH, and the leaving group left, you would have gotten a carbocationic intermediate, which via a 1,2 methyl shift could have rearranged to a more stable tertiary carbocation. And therefore, you would have expected elimination products not only from the non-rearranged carbocation, but also from the rearranged carbocation. And here are those elimination products. This isn't new, this is something you saw last time. To avoid this fate, we're gonna have a new reagent. You're gonna wonder, why does this reagent do elimination instead of substitution? And again, this is just empirical, it just works, we don't know why. Effectively, it turns the OH into a good leaving group. That reagent is POCl3. People call it POCL. You also need pyridine. The POCL reagent itself looks like this. Effectively, this turns the OH into a good leaving group without the leaving group leaving and without a substitution reaction. And then the pyridine does an E2 reaction. And because it is E2, the usual constraints apply. That is, the beta proton must be anti to the leaving group. But the product is exclusively that alkene, and you see no rearranged products. All right. So if you want to see what the structure of that good leaving group is and how the OH becomes the good leaving group, it's in your text. The details don't necessarily help, and so we're just not worrying about them. Yeah?
So you're saying this reaction goes too fast for rearrangement to happen?
It doesn't go, yes, in a sense, there's no rearrangement because there's no carbocation intermediate.
Oh,
Yeah. Okay. Yes?
Would the intermediate with the good leaving group is not a product, right?
The intermediate with the good leaving group is not a product. No, this goes on to the elimination. Yep. Okay, there's questions you could ask there like, well, why doesn't Cl minus come in from the backside and why don't we get inversion of configuration? Why do we go on to an elimination product? The fact that this works is, again, mostly empirical. There may be answers for why it works, but they're beyond the scope of what we want to deal with. Okay, so that was 4 new reactions today, and you can use the method that I talked about earlier if you need help memorizing what to do. If you're going to do this, choose reactions, choose starting materials where there's stereochemistry to keep track of, so that you can keep track of these issues of whether it's SN2 or and the various inversions of configuration. Now, the thing we want to do with our remaining time is to talk about a class of molecules that are called epoxides. And we want to talk about these because these are examples of when it's okay for OR minus to leave. The whole theme of chapter 9 has been that OH minus or OR minus, a negatively charged oxygen, is a terrible, horrible, no good, very bad leaving group. Epoxides are the exception that prove the rule. An epoxide is a 3-membered ring containing an oxygen. An epoxide is an ether. We'll call this carbon 1 and carbon 2. An ether is any molecule in which an oxygen is attached to 2 carbons. It just so happens that in an epoxide, those 2 carbons are attached to each other. There are a couple of different ways you could choose to draw an epoxide. This is one of them, where the bonds of the 3-membered ring are all in the plane of the page, and then the CH bonds are dashes and wedges that are angled down towards the bottom of the page. If you wanted to, you could also draw this same epoxide where the 3-membered ring containing the oxygen is tipped up out of the page. One of the hydrogens is angled down into the page as a wedge, and then the other hydrogens are here in the plane of the page. From time to time, it'll be convenient to draw epoxides in either of these 2 ways, and doing so is generally fine. The defining feature of the epoxide is ring strain. The internal angle of a triangle, an equilateral triangle, is 60 degrees. So the bond angle is constrained to be 60 degrees here. But ideal angle for an sp3 carbon is 109. And so you're pretty far off of that. Meaning, and that means the ring is strained. The carbons are having to distort their shape from the ideal. And so that allows the following to happen. You can have a nucleophile attack an epoxide, and the nucleophile will attack the epoxide in SN2 fashion. So we'll call this SN2 epoxide opening. And it happens with inversion of configuration. Now, this maybe should give some of you a little bit of heartburn, because you'll notice that when the nucleophile attacked, the thing that left, the leaving group, which was this thing, here's your nucleophile, the leaving group that left is OR minus, which you've been used to as thinking about as not a good leaving group. But the fact that it's leaving is fully paid for by relief of ring strain, and by the fact that shortly after the ring opens, the negatively charged oxygen can pick up a proton from some source. I'm just being generic about that source. HA could be water, or it could be some acid. The effect of epoxide opening is going to be to give you a structural pattern that looks like this, where you have an OH on one carbon and a nucleophile, whatever your nucleophile was, on the adjacent carbon. So anytime you see a 1,2 nucleophile OH substitution pattern, that is a clue that you could have made that as the product of epoxide opening. So as we talk about epoxides, we need to deal with a few things. First is stereochemical outcomes. The mechanism is SN2 with backside attack. So we're going to need to figure out how to deal with the stereochemical outcomes of that in epoxide opening. It's nothing new, it's just a slightly unfamiliar context. It's sometimes difficult to visualize, so we'll go through some examples. The second thing we need to deal with is that the epoxide has two carbons that could be attacked. In this case, I chose an example, carbons 1 and 2 are equivalent to each other, but there will be cases where they're not equivalent to each other, and you'll need to know which one gets attacked. That's an issue of regioselectivity, or selectivity among constitutional isomers. So you're going to need to master both the stereochemical and the regiochemical issues associated with epoxide openings. So the one example I want to leave you with is this one. I'm deliberately choosing this example so that carbons 1 and 2 are identical to each other. And we're going to open this ring, epoxide ring, up with MEO minus as our nucleophile. And we'll do this using MEOH as our solvent. We'll show this happening as MEO minus attacks, we'll say carbon 1 from the backside. And the way that we'll show inversion of configuration is to show the leaving group here, the nucleophile here. The carbon that has the leaving group is going to be unchanged. And then the carbon that was attacked, we're still going to have wedges and dashes as they were, but now they're angled up towards the top of the page instead of the bottom of the page. And that's where we're going to have to leave it for today. So we will finish epoxides next time and also move on to chapter 10.